Welcome, everybody, to this sixth episode of Airborne on Air. My name is Marcus Kramer, CTO of Airborne, and today we have Martin van Onna from Strohm. And Strohm used to be Airborne Oil and Gas, so we are former colleagues. Martin, welcome in this webinar.
Thank you, Marcus. Great to be here.
Good to have you. So before we start the content, there are two things I would like to mention. Below in the screen, there's a chat function, and you can use the chat function to introduce yourself and your company to the rest of the audience. There's also Q&A. So if you have questions, just put it in the Q&A, and then we'll try to answer them during the webinar. So Strohm is a company involved in pipes. You see it in the background of the photo of Martin. Composite pipes and then in thermoplastic composites. So we'll talk all about that, and Martin will also have a presentation. But before we go there, I would like to start with a small poll for the audience to fill in. So Dorothea, can you start the poll? Okay, so we'll talk today about thermoplastic composite pipe. And the question is, what is the main driver? Thermoplastic composites are good in high temperatures. Thermoplastic composite pipe is spoolable, leading to lower offshore installation cost. The third is thermoplastic pipe does not corrode and therefore has a lower CO2 footprint. And the fourth is thermoplastic composites are more ductile and better suited for offshore use. Think of impact resistance, for example. So if you can give your inputs, then we'll see what the results are, and then Martin can explain how it really is. Martin, what's your role at Strohm?
I started in 2007 with yourself, running the business unit. And since we are an independent firm, I am the Chief Commercial Officer with a strong technical input and commercial input into business and product development. So that's my role. I cover commercial, business development, sales, making sure that we introduce and successfully roll out our technology across the energy space.
And are you educated as an offshore engineer?
No, I'm educated as a aerospace engineer from Delft, Holland. So the combination of a technical background and some knowledge on composites helped me to work with this technology in this space.
Yeah. Okay, Dorothea, can you show the results of the poll? Okay, the first answer has not been picked, and then there are two ones that are a bit equal. TCP is spoolable, and the other one is that it doesn't corrode. So, Martin, what's your view? What's the main driver for this technology?
Yeah, I think the main driver is indeed the one that was voted upon most. Funny enough, even though there are many coatings available these days, corrosion still is one of the biggest issues in the oil and gas industry worldwide, especially offshore, of course, where up to today, more than half of all the leakages in the energy industry that occur are linked to corrosion.
Exactly. And number two is also important, spoolability.
The spoolability is important because when we developed TCP in Airborne at the time, we really understood, of course, that we needed to create a strong competitive case as well, which in our case really revolves around what we call total installed cost. That is the capex for the operator that buys the system and has it installed. So a composite, the material might be somewhat more expensive than steel. The project as a whole is more cost effective.
Yeah. And spoolable pipe and thermostats are not really an option, so therefore thermoplastics have been used. Yeah, maybe it's now good to go to your presentation and explain a little bit more about the technology. So I'll hand it over to you.
Thank you, Marcus. Can you see the screen?
Yep, we see it.
This is a nice example of a system we installed for Chevron in Angola, offshore Angola. Let me move to the next slide. So this is really what we have developed. We used to call it the one material concept, or one polymer throughout the wall of the pipe. So what we have in this example here, we have one polymer as a liner, so the fluid barrier, in this example polyethylene. We then have a fiber reinforcement that consists of glass fibers impregnated with the same polymer, melts fuse around the liner one by one, and as a final step, the coating again melts fuse on the pipe. So what we create is a pipe that, by virtue of using polymers, is spoolable, is robust, can be handled in a rough offshore environment, but can be spooled. The polymer being ductile allows us to make these systems in lengths of up to 5,000 meters per spool, enabling very cost-effective installation, reducing the overall cost. So a combination of lower capex and lower opex, and as a last point, lower CO2 footprint as well. We then develop different solutions, different material combinations. In the middle, we see nylon with carbon nylon and a nylon coating, one of the best solutions for hydrogen applications. So that's the energy in transition space. And further on the right, what we call PVDF, a fluor-based polymer, very chemically resistant, also nice and heavy for us, again with a carbon fiber reinforcement that we use for the most advanced applications. Now, so just as an example, a few products that we have developed. What you see here on the right bottom is what's called a riser, bringing the hydrocarbons from the seabed up to the floaters. And as you saw in this little animation, very dynamic, very rough environment, fatigue loading, but also clashing. Typically, there are 20, 30 of these risers suspended from one of those vessels. So one of the highest end applications in the industry. That is one that we are developing as we speak. But what we already have in operation around the globe is short connections between wells and platforms, and longer connections between wells and platforms, or platforms and the shore, long flow lines where we have seen the benefit of quick installation with long lengths of pipe. With this, we are not only the first company in the world to have developed this technology, we are also now the company which has by far the largest track record in the world, which is key in the oil and gas industry, where everybody is running to be second. Now, moving further from the oil and gas industry to the energy and transition space, we have done a lot of work over the past years. We are, as an organization now, carbon neutral, climate neutral. On top of that, we have been able to work with our clients to actually measure the fuel consumption during installation. In this case, offshore Angola as an example, where through our work, we found that we can really reduce the footprint, the CO2 footprint of a pipeline drastically when compared to steel, and even more when compared to flexible pipe. This obviously is very important these days when discussing things like the verdict from Shell, for instance. So in that example, Shell is now promoting us to all of their 30,000 vendors to help their vendors to reduce their footprint, and as such, reduce the Scope 3 footprint from Shell. So moving from decarbonizing, helping to decarbonize the oil and gas industry, we then take advantage of our track record and our qualifications to move in the carbon capture, utilization, and storage space, where we are now actively engaging with clients who are using depleted gas fields to inject CO2 offshore, either through a pipeline, like the Portos example in Rotterdam, or using barges or vessels to inject further out offshore. Then the last development we see here on the right is hydrogen. Hydrogen is something we are particularly passionate about. It's going to be a major player in the energy transition, in the future of energy, not only hydrogen, but also ammonia, of course, which is hydrogen based. And what we see is that we have a fantastic technological, economic fit in this space, because we have no embrittlement, no fatigue, and can be pulled directly into the wind tower. Now, one thing we thought was nice always to share is our production. You can see here a interesting close up. We developed in Airborne at the time, now Strohm, we developed our manufacturing technology ourselves. A key differentiator to some other companies who were working on the same technology. GE is an example, who have similar technology, but did not get as far as we did. This is a true example of frugal engineering with a small team doing the right things to come to a robust system in which we have continuous quality in long lengths of pipe. What you see here, we start with the liner. In this picture here, example, polyethylene. We then apply the tapes with a tape winder. You just saw it running. We apply the tapes, one full layer, but there's always some flexibility in there, of course. And then we melt that to a solid wall pipe. And as you can see here, this is literally aerospace grade of pipe quality. It is such a good quality that we are able to qualify our pipes based on the material data that we know on coupon level. So taking that to the last slide, we just try to capture in one slide how we design our systems for application, and we call this digital prototyping. What you all know, the approach of understanding your materials, understanding how the stiffness of the material is influenced by strain, by temperature, and by fluid, as well as time. So we understand in detail how our fibers and our polymers behave under influence of those elements. We are able to predict that accurately. We use that data, both the stiffness as well as the strength, in our FEA approach, where we take the application that we understand in detail. You see the example on the right. We take the application, we take the installation, and our whole system, which includes a pipe with an end fitting for load transfer at the ends, where we take those loads, and based on the data that we have and the predictions from stiffness and the influence of for instance, fluid and temperature, we understand when the system fails, and we can predict that in detail. That is what we qualify and validate in with real life testing. This is an example of a tensioner that is used on board the vessels to transfer the pipe to lay them on the seabed. And here on the right, where you see where we move from a digital prototype to the real system as delivered and as it will be installed on the seabed. That's it, Marcus, back to you.
Yeah, perfect. Good timing as well. So Interesting presentation. I've also seen some things that are new to me, so that's always good. Maybe you get a little bit impression. What kind of pressure ratings are we talking about?
When we look at our at composites, we can do pretty much anything, right? We can go to the highest pressures possible. Today we are up to 860 bar for small pipes. For larger pipes, so where we go to 6-inch or even bigger, 7-inch, we can achieve 10,000 psi, which is 689 bar. So that's the internal pressure. Composites are often known to be somewhat limited when it comes to compression, right? We however see that we have very good performance on compression as well. So typically we can go to half the internal pressure, so to speak. So we can go to 3,000 meters water depth, and still be able to handle the external pressure, which at 3,000 meters is 300 bar.
Yeah, and these numbers are all design pressures. So the pipe can have more than the design pressure. So I believe it's up to around 2,000 bar or something.
Yes, it's around a factor of 3.5, typically 3.5, sometimes even 4. So an example of a system we just applied to Shell in US, that was a 10,000 psi, so 690 bar rated, but the burst levels was around 3,000 bar.
Yeah.
So that is quite significantly above the design pressure.
And if you bend the pipe, the interesting part is, of course, that this is a very long pipe, some kilometers of length, and then you put it on the reels that are in the back of you. What kind of strain do you apply? What kind of bending radius is possible?
Good question. That depends a little bit on the fiber angle, right? Because the fiber angle determines the compressive stress that we introduce into the pipe. So when we have flexible pipes that do not need to have high tensile strength, we go up to 3.5%, 3.5% strain. So that means that we can put a 6-inch or a 7-inch pipe on a 7-meter diameter. However, when we have those pipes, they need to be suspended from vessels down to the seabed in deep water. So very high tensile strength. Then we need fibers almost in the direction of the pipe. And then we reduce the strain levels. Then we are typically around 1%.
Okay. I have a question from Mr. Alper Aktas. He asked about pressure ratings. We talked about it, but also temperature ratings for hydrogen pipes. What is possible? And I assume it's the upper limit, but also the lower limit because it's hydrogen.
Yes, that's a very good question. So to start with the higher end, depending on the polymer we use, we can go up to 120 degrees Celsius typically. So on the upper side, there's not much of a limit. On the below side, we actually look at the glass transition temperature, because we try to stay away from that. So for glass polyethylene, we can go to -60 without a problem. So glass polyethylene gives us a -60 +60 limit typically. We also have looked at polymers in the past. You may recall that, Marcus, for cryogenic applications, where we are also working on. And there are polymer solutions available to us that can bring us to -196 degrees Celsius.
Yeah. Good answer. I have a question from Mario Saba. Hi Mario, good that you're in the meeting. And his question is for subsea pipeline application. So I assume that's flow lines. Is the wall thickness more driven by the internal pressure or by the tensioner loading? And then he asked, for example, do you install the TCP pressurized?
That's a very good question, Mario. I would not have expected anything less from Mario, of course. And it's a very good question. And in fact, in some cases, the tensioner loading, so the installation case, can be quite important. Can be a very important load case. In our case, fortunately, it is not driven by tensioner, and the wall thickness is mostly driven by internal pressure, sometimes by external pressure. So, for instance, when we have 6-inch ID, I have it here. I have one. If you see this one,
Yeah.
this is 5.2-inch ID. And in this one, it was driven by the external pressure because it had to be qualified for 3,000 meter water depth. Now, in such case, the installation is not a challenging load case anymore, and we never have to install the pipe pressurized.
Okay. Good. And then I have a question from Mr. Nishiyabu. He asks, what about the orientation of the carbon or glass fibers in TCP? What kind of orientations do you use?
Yes, that's also a very good question. So depending on the requirements, if we have a flexible pipe that does not need to have high tensile strength, then we use a plus or minus 55 degrees. However, we change it slightly through the wall of the pipe so that we avoid a stress peak, and we can handle the highest pressures and even have the fibers on the outside still carry a lot of load. So we typically move from the 60 to the 50, right, degrees, but on average it's 55 degrees. On the riser, so high tensile strength, there we move to a fully fiber dominated design, which is plus or minus 35, balanced with plus or minus 80. So we have plus or minus 35 or plus or minus 40. So in the direction of the pipe. So those fibers handle the high level of tension loading as well as fatigue loading, of course, and that is then balanced by plus or minus 80 degrees. We always try to avoid, as you know, stiffness jumps, right? So we always create a balanced layup of the system.
Yep. Okay, we have also two people that want to ask a question, let's say, in the webinar itself. The first one is Mike Buck from United States. I hope Mike is there. And Dorothee, if you can put him on, also with the camera, then Mike can ask his question. And Mike, we know already a long time. Mike is from the 90s. We have been in contact. Hey, there's Mike. Now you need to switch on the camera and your microphone. Hi, Mike. How are you?
Very good. Very good. How are you guys doing? It's been a long time.
Yeah. I was just explaining that we met, I think, in the 90s when you were developing the tapes that we wanted to use for pipes. So there's a long history.
Yeah, absolutely. I think actually, Marcus, when we started our business, I think you guys were either a second or third contact. So you guys have been doing some great work. I really appreciate it.
Yeah. And you had a question for Martin.
Yeah, I was curious as far as how does Strohm handle the spacing of the composite prepregs in the long flexible pipes?
How do you mean, Mike?
Yep. Hey, Martin, how's it going?
Say again, Mike. I didn't get that question. Can you explain?
Sure. Yeah, what I was wondering is how does Strohm handle the spacing of the composite prepregs in the long flexible pipes?
Yeah, we do it like this. Here, let me share the. So what we do is we actually always create one full layer, right? So what you see here this is exaggerated. Can you see this or not?
Yep.
Yep, I can see it.
In principle, what we do, and I think I understand maybe what you mean. I know one of our competitors does this differently. Our tapes are in principle so wide that per pass, we create one full layer. So we create one full layer, and our melt fusion station is designed such that if there is, for instance, a space, that space disappears in a melt fusion station. So this is where we see that after the melt fusion station, the whole pipe is without spaces and without voids.
Oh, okay. So you plan on to either bud or have a small space so that the polymer can flow and fill and create a full layer by layer?
Correct.
Yeah.
Yes.
Oh, terrific.
Correct. And we measure the space automatically as we go, and the taping heads can adjust, right? So that we keep the spacing within, let's say, the tolerances that we know we can, call it fill up in the melt fusion station that's behind it.
Oh, terrific. Thank you.
Thank you, Mike. Very good. Speak
welcome.
to you soon. We have a next question. Xavier Montibert from Plasma Bound, who has a question about the end fittings. Is Xavier available? Yes.
Yes, good afternoon. Very good presentation, Martin. Thank you very much. I'm Xavier Montibert. I'm the commercial director for Plasma Bound, and we have developed a breakthrough technology to automate the surface treatment of composites, polyester, for example, before bonding, better join similar or dissimilar materials. And I was wondering, is this something that you are also facing as a problem, surface treatment? How do you connect your pipes to metal? Please share.
I understand. Thank you. Yeah, this is really why we used what we called the one material concept, right? By having one, like you see here, one polymer in a liner in between the fibers as a matrix and the coating, we actually melt it together. So that creates a bond that is as strong as the material itself. So in that sense, we do not use adhesives. We are using on that we are not using adhesives. We are using adhesives in a system where we use what we call a permeation barrier in hydrogen, which is aluminum wound, where we have between the liner and the fiber pack, we have a aluminum barrier wound. There we do use a adhesive system. In our end fittings, we simply clamp our end fittings. That's one of the nice benefits of polymers, right? They are ductile, so they allow us to simply clamp like a garden hose, clamp our pipe. Does it answer your question?
Yeah, and hydrogen, you don't use any surface treatment either. No need, or
well, so in hydrogen, where we apply this permeation barrier, there we do have an adhesive. But as far as I know, we do not use a surface treatment to that liner.
Okay.
That may be something to consider. So do reach out to us if you wish.
I will do. Thank you, Martin.
Thank you, Xavier. Very good.
Thank you.
And then we have a question from the previous speaker, Leif Asp from Chalmers University. Dorothea, can you put his recording on when he asked the question? Oh, what happened?
I also saw a question from Noel still, Marcus.
Yeah, here we see the question from Leif. I'm looking a little bit to the time.
Okay.
Can you start it, Dorothea?
So no, Actually, I wanted to ask him about the inertness of PVDF. I know he uses PVDF, and due to the inertness of this PVDF, adhesion to carbon fiber has always been a challenge. So I wonder how he tackles this.
So the question is about adhesion between the fiber and PVDF.
Yes, and that's a very good question, of course. PVDF being a fluor polymer, and the adhesion was a critical element in our product development. We engage with our supply chain partners on this topic, both Barflex, Barday in combination with Arkema, as well as Solvay, and indeed the connection between the adhesion between the carbon fiber and PVDF was a critical element in their development, crucial to the success of the riser product as we have it now, and we solve that by having a functionalized PVDF that enabled us to create a very good bond. This bond is important, especially for the compressive strength of the system, which gave us a pipe system that can be installed using small vessels, existing vessels. So we needed a certain minimum bend radius, and with that translated that to a compressive strength. So it is a functionalized PVDF that allowed us that allowed our supply chain partners to solve that challenge.
Yeah. Okay, very good. So it's really in the material processing to make tape. So then we have two questions left in the Q&A that go about the connections. So you talked a little bit about it, the end fitting, the metal end fitting. But how do you certify? And is there maybe also a problem in different CTEs between metal and plastic?
Yes, thank you. Our system has actually never, our end fitting system has never fundamentally changed. We simply clamp our pipe. So we have a stem on the inside with a very tight tolerance fit, and with a sealing system there. So there can be O-rings, can be lip seals, can be a variety of seals depending on the surface that we anticipate. On the outside of the pipe, so straight onto the coating, we apply wedges, steel wedges, and then a sleeve, and we clamp the system in that manner. So this approach allows us to create a connection, an end fitting that we can apply anywhere around the pipe. We can apply that offshore as well as in the factory. And because we can clamp, we do not need to weld. We don't need epoxies. We don't require hot work. And this is probably for some of our clients in the offshore business, one of the biggest benefits compared to other solutions. So we have always applied a clamping system.
We're now at the end of the. You can of course reach out and we'll try to answer them for you, Martin. Thank you all for being here in the webinar. Thank you, Martin. This ending the current series before summer. We might come back after summer, so keep tuned. And thank you all. There will be a feedback poll at the end so that you can fill it in and we get your response. And for now, I would say thank you to everybody. Thank you, Martin.
Thank you, Marcus.